Okay, now for part 2 of this question. Okay, and we've already answered part A. Okay, part A, we had to find the acceleration. It's part 1, sorry. We had to find the acceleration and the tension in the string. Okay, like before the string broke, basically. So the system was released from rest. What's the acceleration and the tension in the string? Okay, if the situation is like this. But then part 2 is about the string breaking. Now, I already showed you how to do part 2 by using basically SUVAT. Okay, now I'm going to show you how to do part 2 or beginning part of part 2 by using like work energy. Okay, to work out something that we need to find out before we answer the question. So basically, the difference now in the question is this part over here, is that they're going to reach the same level. It says when A and B both reach the same level, the string breaks. So we got to first work out the situation when they reach the same level. Right, so they're going to be at the same level when B and A have both traveled the same distance, and that distance, as we discussed earlier, is basically half of the difference between their heights. Okay, so basically their difference between their heights is 1.75 minus 1. If we divide that by 2, they'll tell us how much they rose and fell by when they reach the same level. So A is basically falling by 0.375 meters, and B is rising by 0.375 meters. Okay, then they'll be exactly at the same level. Okay, and what we need to find out is the speed of A and B at that point when they reach the same level, because that's when the string breaks and that's when the new situation arises. Okay, so basically we're going to work out what that speed is, and in this case we're going to use the work energy principle. All right, so we know that the total kinetic energy at the start, plus the potential energy at the start, okay, plus the work in, okay, is equal to the kinetic energy at the end, the final kinetic energy, plus the potential energy at the end, the final potential energy, plus the work out. In this case, there's no work in, because it's just there's no like pulling force. Okay, it's all work done against gravity here, so that's included in the potential energy. And there's no work out because no tension, there's no friction, and there's air resistance or anything like that. So we just have a simple kinetic energy at the start plus potential energy at the start is equal to the kinetic energy at the end plus the potential energy at the end. For A, it's between these 2 points. All right, so we're going to take this as our 0 point. This is going to be where potential energy is equal to 0. Okay, so A is above that. So A is not moving at the beginning, at the start. A and B are both not moving. All right, so the total kinetic energy at the start for A is going to be 0, and for B is going to be 0. They're only both going to have potential energy. So for A, the potential energy is going to be mgh. So remember, potential energy is mgh, and kinetic energy is a half mv squared. So for A, okay, it's above that level. So for A, it's going to be m, which is 1.3, times g, which is 10, times h, which is 0.375. But for B, the potential energy of B, it's below that level. Okay, so it's going to be its mass, which is 0.7, times g, which is 10, times minus 0.375. And that's going to be equal to the kinetic energy of them both at the end, which is going to be basically when they reach this level here. When they reach this level here, the potential energy will be 0. In this case, this is going to be 0. In this case, this is going to be 0. When it reaches O, the potential energy is 0 for both of them, because they're both at the level which we've said is 0 level for potential energy. But A is going to be moving at a certain speed, okay, and B is going to be moving at the same speed. But So the velocity of A here and the velocity of B here, the magnitude of the velocity of A is the same as the magnitude of velocity of B when they reach that level, because they're connected with the same light inextensible string. So we're going to have a half mv squared. All right, so it would be a half times the mass of A, which is going to be 1.3 times v squared, plus a half times the mass of B, which is 0.7 times v squared. Okay, that v is the same in both cases. So let's see what this gives. So here we're going to have, that's going to be like 13 times 0.375, 13 times 0.375, and you're going to have plus, and you're going to have, that's like 7 times negative 0.375, which gives us 9/4. That's 9/4 equals, and this is going to be half of 1.3 plus 0.7. That's going to be 2. Half of 2 is 1. So it's going to be v squared. Let's just make sure of that. That will give us exactly the same answer then, you see. So you have 1.3 divided by 2. Divided by 2. Okay, plus, because it's the same v, 0.7 divided by 2. Which gives us, hold on one second, 1.3 divided by 2. Okay, plus 0.7 divided by 2. That gives us 1. That's right. Okay, that's 1. So v squared equals 9/4. Therefore, we can say v is equal to 1.5 meters per second. So that's the velocity of A and B when they reach that level. And then the rest of the question is the same as what we did in part in the other method. All right, the rest of it is the same, working out the time it took for them, the difference in the time that it took for A and B to reach the ground. So I'll just go through that quickly again. I've explained it here, but basically this is the other way of working out their speeds at that point where the string breaks. Now, after the string breaks, A is going to go directly to the ground, heading downwards. It starts at 1.5 meters per second. It's going to hit the ground. So we don't actually need to know that time, because when B goes up and then comes down again, it's going to go from here to there with the same time, because it's going to be going up with a speed of 1.5 as we just calculated, and it's going to reach the top of its flight, and as it's coming down, it's going to be going down at this point back with the speed of 1.5 meters per second, but downwards, right? And from this point down to the ground, it will be the same time it takes for it to reach the ground that A reached the ground when A started. So all we have to do now is work out how much time it took for B to go up to its highest point and then come down to this level again. That's the extra time that B took to reach the ground. So we used SUVAT for that. As I mentioned, we want to find the time for the displacement from this point for it to be 0 again. So it's going to start at 0, it's going to end at 0, okay, because that's the same level. But on the way up, it's going at 1.5. On the way down, it's going at minus 1.5, because we're going to take up as positive, because it's initially starting. We always take the initial kind of movement as our direction. That's how I like to do it. So we're taking up as positive, right? So it's going up with 1.5. That means when it comes back down to the same level, when the displacement is 0, it's going to be going down at minus 1.5 meters per second. The acceleration is due to gravity. We've taken up as positive, so down is going to be negative. So A is negative 10, because acceleration due to gravity always acts downwards. And then we can see the only thing we need to find is the time. So here we have got V equals U plus AT, and we found the time, right? So the thing that's different about this particular section that I've added is the fact that we have found the speed with which it reached, the speed with which they reached the same level when the string broke, using work energy. That's all. That's the only difference, right? So this is the addition, which I'm going to save in the separate, separate playlist. So if you want to see more details about the beginning of the question, part 1, okay, then you can go to the playlist for this paper, which will be found at the end of the video at the top here. Click on that and you can go and watch. This is question number 4, okay, from this paper, right? So I've answered this as a separate question, okay? okay, so that we can save this under work energy principle. So that's the answer to this question. Thank you for watching. Hope that was clear. Other questions from this paper, as I mentioned, can be found at the top right of the screen at the end of the video. Other questions from work energy principle you'll find in the playlist over here. In fact, I'll put a link to the video for the rest of the question, part 1 and so on. You'll find that over here, plus the other way that I answered the question, this particular part. And you can subscribe to the channel by clicking on this link. Thank you for watching and see you soon.